Right. So today we're taking a look at mechanical properties of matter. Right. Quick things that we need to remember. We need to remember about density. How you find density there, Shivish? How you find density? M over V, correct. Mass per unit volume. Right? SI unit is kgm to the minus 3. Right? And we need to remember what is relative density. What is relative density? Density of substance over density of water, or density of substance A over density of substance B. Actually, you don't really use that. You're using mass. Right? Our next version that is used sometimes is mass of substance over mass of an equal volume. Mass of an equal volume of substance. Right? So those are two little things I need to remember about relative density. SI unit, none, right? No SI unit, right? Right, next thing we have to remember pressure on a solid. Pressure on a solid is force acting per unit area, SI unit pascals, or what's the next one? Newton per meter squared, right? Or you had one kg, right? What's the formula for pressure in a liquid? Huh? So we had proved that. See if we can prove it now. Should we do it halfway? Huh? All right, so see if we can prove pressure in a liquid now. I'll give you a little startup. Right? I'll give you a little startup here. P is equal to F on E. Oh. Right, so you have a little area here. What's it? Well, you can put in all them things. You have height, you have your density and thing, right? How are you going to prove pressure in a liquid? You know the formula. Pressure is rho GH, right? How are you going to bring that in here? Okay, we have 2 minutes. Start up right there with forces. Pressure is force on area. Should we show you bring here, boy? What fruitcake? here. What are you showing? Right, remember we stop in it, right? Destiny, Destiny do no labs. She do any labs? She was in Unit 2 for the first day. All right, we gotta finish all those Unit 2 message order, right? I'll tell you. I did the unit. Oh no, I thought that's one project, but that's to do. You want to do the Unit 2 project, I forget the Unit 1 project. Before we do that. I see everything. No. Have a boy doing Unit 1 out of it. Right. Y'all done? Right. So what is the force exerted? The force exerted on that little area down there is well the weight of the water, right? Correct? The force exerted down there is really the weight of the water on that area. So it's mass of the fluid or water by gravity all over the area. That's okay? How you find mass? Mass is what? No, but then you're going back in circles. In terms of density and thing. Mass is what? Right. Remember density is mass by volume. So it means that mass is density multiplied by volume. So I could take off this mass here and write density of the fluid by the volume of the fluid. So now pressure is equal to density of the fluid by the volume of the fluid by gravity all over area. See, we can finish it up now. See if we can finish it up there. Oh, yeah, take a minute, right?
I was working on that. What?
Right, so Azaria is requesting. Azaria not paying attention, so you see what she wants to do? She wants to summarize everything. So she wants to use the AI companion to summarize everything. That is true. Right? So volume is what? Volume is area multiplied by height. Right? So the A will cancel, and you will get pressure in a liquid is density by gravity by depth. Huh? She know it is like a Google that. But it'll be accurate. Okay, so those are some of the things that you should know from Form 5, right? Well, accept the proof. Accept the proof. Right, so after we do this now, we could go into Hooke's law and thing, right? Let's take some notes here. So the next heading that we're looking at is deformation of solids. Right, forces applied to a material may cause it to become deformed. Right, what does that mean? It means that the material is said to be stressed. The material is said to be stressed. And as a result, is said to become strained. Right, there are two types of stress that we need to know. Tensile, right? Tensile stress, increase in length, and compressive stress, a decrease in length. Right, tensile and compressive, right? I should have just finished type for this one. I don't have it again, huh?
Down or just straight?
Huh?
From A to B, down or straight? Down after straight, no?
And a straightish.
And that's supposed to be
So choice straight. Choice straight. Huh?
It's supposed to be straight. Is rotate.
Yeah, that's straight line, yeah. O to A, that's straight line earlier. Let's hook slow, it's gotta be straight.
I now realize that the straight too.
Well, it's a 3 hand.
I'm straight too. I'm straight too. Yeah.
Huh? Yeah, just turn the light. Wait open. Who? Aline. Who? Who? Yeah. Right, just two quick definition I talked to you about already. Stress is force acting per unit area, strain is extension per unit length. No, one is stress and one push-ups. Thanks. It's stress versus strain. Sorry about that. Stress versus strain graph. Sorry. What's that way? It's like the kind of like a 6, but it's not going up. It's going like an apple. Sigma. Come on, sigma. Next one is a kind of fun looking E, right? Curvy E, but come on, not capital. common. So stress is force acting per unit area. Strain is force per unit length. Right? Then we're going to explain each part, right? Huh? Like, yeah, but common. Not the capital. Hmm? Everything have common and capital. All Greek letters have common and capital. Okay, so that. It's very useful to keep it in. All right, nice. Ready? Let's take a small note just to explain O to A to B, B to C, C to D, and so on, right? Quick note. O to A is a straight line. O to A is a straight line. Online? Are you okay? Alena?
Yes, sir.
Azaria, paying attention? Okay. Right. O to A is a straight line through the origin. O to A is a straight line through the origin. Where stress is proportional to strain. What do I write down again? Okay, well, tell me what's the A to B then, and then B to C. Well, write it down so you will know. Right, O to A is a straight line through the origin. Stress is proportional to strain, and Hooke's law is obeyed. And Hooke's law is obeyed. Right? Well, what is cool relationship here, right? We said stress. We said stress is proportional to strain. We know stress is force over area. And we know that strain is extension over length. But remember, A and L are constants, correct? A and L are constants. A is the cross-sectional area, that won't change. L is the length, that won't change. But force and extension would change, right? So basically, you can take off A and L, and you will see that F is proportional to A. Which law is that? Hooke's law. Okay? So basically, based on this relationship, you will see that Hooke's law. Oh, sorry. F is proportional to E. Let's write that, right? Jeez. F is proportional to E. Hooke's law. Right? So the Y obeys Hooke's law from O to E. Right? O to E is a straight line and Hooke's law is obeyed. Stress is proportional to strain. Right? A is the proportional limit. A is the proportional limit. A is the proportional limit. Beyond which Hooke's law no longer obeyed. Beyond which Hooke's law is no longer obeyed. Beyond which Hooke's law is no longer obeyed. Huh? I just not over there. A is the proportional limit. A is the proportional limit beyond which Hooke's law is no longer obeyed. A to B is called the elastic limit. A to B is called the elastic limit. A to B is the elastic limit. Full stop. If the elastic limit is exceeded, if the elastic limit is exceeded, if the elastic limit is exceeded, then the material does not return to the original. Then the material does not return to the original shape and size. Full stop. O to B, B as in boy. O to B is elastic deformation. O to B is elastic deformation. The point P is where plastic deformation begins. The point P is where plastic deformation begins. Plastic deformation begins. The point P is where plastic deformation begins. Right? Beyond, full stop, beyond P, beyond B, the material is permanently strained. Beyond B, the material is permanently strained. Permanently, right? Permanently strained. Right? Next one, B to C, plastic deformation. B to C, plastic deformation occurs. The point C, maximum stress. The point C, maximum stress. And the point D is the breaking point. The point D is the breaking point. All right. So those are the things that we need to know. The last quantity that we have to look at is called Young's modulus. The last quantity that we need to know is Young's modulus. Right? Young's modulus, its symbol is 0.8. Huh? Yeah, that's 2.5. Young's modulus is capital E. Right? Young's modulus is capital E, and is the ratio, right, is the ratio of stress to strain. So Young's modulus is equal to stress over strain. Right, stress over strain. Right, you'll also notice that you might see the formula looking like this sometimes. Stress is force over area divided by extension over length. A little bit of maths and you can switch it up and you'll get F on L all over A by E. Right, remember the division sign was switched and multiplied and so on, right? So Young's modulus is also FL A on E. Right, SI unit. What will be the SI unit, Olya? What will be the SI unit for Young's modulus? Squared or pascals, right? Yeah. Yeah. Oh wait, you want to use the charger? I mean the port. All right, quick question. I want you to note. In fact, I'll ask you a question. See if we can figure this out. I'll give it two versions actually. Suppose I gave you a graph, right? Suppose I gave you a stress versus strain graph. And it's a nice straight line. What's the gradient? On the other hand, that's option A, right? Option B, I gave you a force versus extension graph. What's the gradient? Look at the graphs and tell me what the gradient in each one is. What will be the gradient of the first graph? Sorry? For the first one? But remember, Right, but in the gradient is stress on strain, right? Which is Young's modulus. So the first graph is just Young's modulus. All right? So for the first graph, the gradient is Young's modulus. Well, what about the second graph? K, right? Yeah. If you use F is equal to KE, then K is equal to F1E, right? So the gradient is spring constant, right? K. Or the material constant, whatever it is. Right, but here's my question to you now. Suppose I give you what you said. This is what you're going to need to help you, right? Suppose I give you a different graph, because when you do past papers, you're going to see a lot of graph questions on Young's modulus, right? So if you see a graph, right, and the graph is a force versus extension graph, same straight line. How do we find, sorry, this is common here. How do we find Young's modulus? How do we find Young's modulus? So it's a force versus extension graph. How do we find Young's modulus? Right, the only hint I want to throw at you is, remember, Young's modulus is force by length by area and extension. Right? We just proved that, right? So I want you to try to figure out how we're going to get Young's modulus from a force versus extension graph. Ariam will help us, right? Right? The hint is to work with that formula there. Multiply by L over E. Not a wrong. Close to it. Close to it. Young's modulus, right? Look, how you find in Young's modulus? Fair enough. Which man am I food not figure out that? What? Any answer online? Okay. You can close it. And you kind of figure it out, but what do you have something else? Online, any answers? Alexia, any answers? Okay, what? Oh, you had it the first, you almost had it the first time. First thing that you said. Anybody online figure it out? Mazavia, you closed it. Can't you anything? Prashant? See you anything? Asira? Yeah, she's the guide now. Right? But I want to see what it like that. That was say was real close. We wouldn't all be gay. We wouldn't all be a material as K now. So you had to find the gradient first. So Young's modulus is equal to F on E, L on E. Right? F on E is your gradient. So it's gradient multiplied by L on E. That'll give you Young's modulus. Okay? So you have to learn to use the formula, right? You can do it like that, or Or you could do some linearization, or you could do it like this. Remember, you have to make, that's your y-axis, that's your x-axis. Multiply, cross multiply, make F is subject. FL is equal to EA by small e. Carry across the L, you'll get EA on small l multiplied by E. So basically, this is your y-axis. This here is your gradient. This is your x-axis. So your gradient is equal to EA on L, which means that E is ML on E. Okay? So if you see this graph and they ask you to find Young's modulus, that's how you're doing it. Actually, work with graph paper next thing. Yeah, so we'll do one at least. We'll do one class in class next week. Copy it down. That's our past paper. All time. So today we're taking a look at quick things that we need to remember. I true. I gotta talk to this man, boy. All right. So what is here? We have a graph. They plotted for you already. Just make a note of the two values on top. Ooh, can I see that? Right? It have two bars on top. The length of the wire, write that down. The length of the wire, 2 meters. And the diameter of the wire, 1 millimeter. Look at the graph. You see the graph there? Question said load versus tension. Well, F over E. No, load is L is length. Look at the SI unit for load. So load is a force, right? That's F versus E. Okay? Now, here's what they asked for first. At what load, it'll be kind of hard for you to read off perfectly, but we'll average, right? At what load did the wire begin to deviate from Hooke's law? At what load did the wire begin to deviate from Hooke's law? What y'all think? Tell me between which dots? Start from the underneath. Here's dot 1, dot 2, dot 3. Between dot 5 and 6. Yeah? So maybe you're wrong right after dot 5, right? It looks like dot 5 is the last one. You're saying that? So we will average around what? 50, 54? 54 also? It's a little lower than half, right? So at 54 newtons, the wire began to deviate. What was the stress in the wire when it began to deviate? How you find stress? Stress is what? Stresses force over area. Right, but what is the force? 54, nice. What would the area be? Pi r squared, right? Pi r squared. And I gave you the diameter. Correct? Diameter was 1 millimeter. Work it out for me now. 2003. Work it out fast. With thing didn't come. Previous income. He wants to line too. So, but look, Alina in class here. Alina. Look, Alina there. See message. How much you all got? Alina, doing your work? Okay. I'm taking a Shivish. What you get for the video? What's the diameter? Did you write it down? Right, so what's the radius? What's the radius? How much all I get for everything? How much? 6 point. 7. What's the SI unit? Pascal. Nice. The one is strain on the wire. How you finance strain again? How you finance strain, Aaron? Strain is what? Extension over length. We know the length, right? How you gonna get the extension? Sorry, yeah. Of the graph. Right? So of the graph. Might be kind of hard, but we'll average, right? The ratio of two same quantities, right? Yeah. What do I want to use? 0.675. Sorry. 0.75. If we had an average, it's like here, right? So let's use 0.75 millimeters. 7.8? No. 7.5. Yeah. And then find this strain, please. Everybody following? You're following for going on, Ariane? Follow what going on? You sure? So we know what it's strain, right? What you all got? The strain on the wire, that pointers. So extension on length, and you all got how much? 6.75 by. Oh. 1 to you, by. 3.75 by. minus 4. And last part, how we get Young's modulus? How we get Young's modulus, Timothy? Huh? How we getting that? We just work out strain, we just work out stress. Stress over strain. That's it. We already have stress and we already have strain. You don't need all that. Remember, you already found the stress and you already have strain. So let's divide it. Alexa again, true? Alexa messages here, boy. Alexa again, true? Okay. Right, so sometimes in a graph question, they'll make you plot it and work all these things out. Okay? Everybody okay with this? To be sure? Right, walk it graph paper next day. Just now, I think I have one more for you. A multiple choice somewhere. Oh wait, no, sorry. What? Oh, it mixed up Young's double slit experiment. Oh, sorry. Don't worry with that. Yeah? Huh? Extension on length, and we got the extension from the graph. All right? From the same load value, we read off the extension, and they gave us the length. In the beginning, they gave in the beginning. All right. So next day we'll go a little more in depth and do some harder ones, and then plot a graph, and finish up with strain energy. Right. Please remember that next week will be